Hi everyone, very good afternoon. My name is Anup Divakaran. I'm a sales manager with Digital Technologies. Now we have the speakers and co-panelists with us on this, all set to kickstart this webinar. But I think we'll give it 2 minutes for other participants to join us. So we will start at 3:33. I hope that's okay with everyone. In the meantime, I'd like to tell you that if you have any questions or anything that you'd like us to address, you can raise your hand. You have that option, or you can use the question and answer section. And we'll have either Satvik, Praful, or Ayush from our team who would answer those questions. Of course, you also have an option to ask us the questions either in the training survey, or you can also email us with any questions that you may have later on. All right, the speakers, Praful and Ayush, can I request you to show yourself and switch on your camera? Thank you, Praful. Ayush, can we see you as well? Thank you, Ayush. All right, very good afternoon, everyone, and a warm welcome to today's webinar on design, test, and deploying wireless systems using MATLAB and USRP SDRs. We're very delighted to have all of you with us as we explore how MATLAB and USRP software-defined radios can accelerate wireless communication, research, prototyping, and deployment. Now, we have two speakers for the session. We have Dr. Praful Pai, who is the manager for electrical and computer engineering at MathWorks. Now, Dr. Pai is a PhD holder from IIT Kharagpur and has worked extensively on mathematical modeling, signal and image processing, machine learning, and hardware prototyping. He currently focuses on advancing MathWorks' approach to signal processing wireless communication in academia by constantly engaging with institutional leadership, faculty, and students and researchers. We also have Mr. Ayush Chandra, application engineer at Digital Technologies. Now, Ayush has great expertise in embedded systems and wireless communication applications. He supports researchers and engineers in adopting cutting edge tools for innovation. And I'm sure their insights will make the session engaging and valuable for all of us. So without any further delay, let's get started and I'll hand this over to Ayush. Over to you, Ayush.
Thank you, Anup. So I am Ayush Chandra. So before we get started, let me quickly share today's agenda. So what we are going to cover in this webinar. So first, we will introduce an agenda overview and introduction to USRP. So next, Dr. Praful Pai, he will guide us through MATLAB and USRP workflow, and he will cover USRP interfacing, over-the-air testing, FPGA targeting, and spectrum sensing and computation, AI for wireless, and next, he will inform us about teaching resources available for academia and training. So, and finally, a summary of how MATLAB and USRP can simplify wireless design and testing. So next, we will conclude with a Q&A session. So please feel free to type your questions in the chat at any point, and we will address them at the end. So this webinar is designed to be informative and interactive. Hope you will enjoy and learn as well. So, okay. So before we get into the agenda, okay, I'm briefly introduce about the company where I'm working, that is Digital Technologies. Okay. So let me share my screen. Okay, the screen is visible to everyone.
Yes, Ayush, you can.
Thank you. Thank you. We are Digito Technologies, which is providing cutting-edge solutions in field of test and measurement, industrial automation, 5G, 6G wireless technologies, and AI-driven IoT-based solutions. So, with a focus on innovation and customer-centric services, we aim to empower industries and research organizations with advanced tools and technologies for seamless development, testing, and deployment. So we are partnered with some of the renowned OEMs. So these are ST Microelectronics, which is working in the field of embedded and providing semiconductor products like microcontrollers, FPGA boards. So next, we are partner with Digiland, which is a national instrument company, which is providing solutions in academic for test and measurement. So basically, it is popular for providing FPGA boards and analog discovery devices. So next, this is National Instrument, which is now part of Emerson Group. It is a well-known company for industries also and academic also. It is providing solutions for test and measurements. Next, we are partnered with Mantis Wave Network, which is India-based company and providing solutions for 5G, 6G, and other wireless solutions. So it is providing private 5G network solutions also. So next, we are partnered with TMY Tech. TMY Tech is a Taiwan-based company which is providing solutions for wireless communications in 5G and 6G. So basically, it works in the range of FR2 and FR3 from 6 gigahertz to 44 gigahertz. Then we are with the Corobot Technologies. It is again a India-based company which is providing solutions for embedded and AI-based solutions in field of robotics. So Imona Times, which is providing, it's an Australian-based company. Okay, it's providing academic solutions, setting up the labs, analog and digital labs, and DSP, digital signal processing labs, and providing solutions for wireless communication, setting up lab at the basic level. Okay, so this is about the partners, which and next. So these are our key expertise where we are providing solutions in terms of automated test and measurement, where the companies like National Instrument, which is providing solutions like they have various platforms like LabVIEW, Multisim, PXI system, CDAC, and CDU. And in wireless, it is having USRP radios, which is providing solutions in different fields, like in civil field, civil department, also mechanical, electrical, electronics departments. So it covers almost all departments from NI. So next we have AI and machine learning based solutions. So we provide edge AI, IoT, vision AI solutions from using ST Microelectronics board. And we have one more company, that is Digiland, which is providing FPGA boards. FPGA can be programmed at any time, and it provides solutions for AI-based solutions also. So next, nowadays, and National Instrument, TMY Tech, and Mantis Wave also started implementing an AI in wireless communication. So next, we are have solutions for FPGA and semiconductors. So STM Microelectronics is the well-known company for providing semiconductors product and FPGA. Apart from that, Digiland is also a big company which is providing FPGA development boards and training tools, making FPGA technology accessible for students, researchers, and engineers. Next, we have 5G and 6G wireless communication setups. So basically, we can talk about National Instrument, which is providing USRPs. So USRP is a kind of SDR, so which is used for designing, deploying, and testing the 5G, 6G wireless test beds and systems. So next company is Mantis Wave Network, which is also providing wireless communications solutions, and then TMY Tech. So Next, we have quantum and optical solutions. So VRV is one company which is leader in optical networking, test, and measurement technologies. This supports industries such as telecommunication, aerospace, defense, and research industries. So going so these are some partners. We have signature customers where we have worked earlier. So this is not the single page. This is multiple page. So I'm just covering in one page. Okay, these are the popular customers which we had worked with. Okay. So next, for what we are here, that is USRP and wireless system design. So we are going towards the wireless system designs. So let me first understand what is SDR, that is software defined radio. So an SDR is a radio communication system where many of the traditional hardware based components like mixer and RF front end implemented in the software. This allows for reconfigurable software based processing and conversion of digital signals. So with SDRs, much of this functionality like analog to is replaced by analog to digital converter and digital to analog converter, which digitize the signal, allowing software to handle modulation, demodulation, filtering, and other tasks. So we can say SDR is an emerging technologies playing a critical role in wireless world, supporting rapid innovation in field like cellular communication, IoT, satellite link, and beyond. So let's see the general architecture of SDR, how it, so this is antenna. So this is antenna, then TXLS, that is transmitter and receiver switch, then radio front end, ADC and DAC, and then digital backend, and then host. So basically an SDR system consists of several keyboards, that is power board, digital board, which is used for signal processing, then timing module, and receiver and transmit module. So basically these boards are interconnected and providing high speed cables, interconnected using high speed cables to ensure fast and efficient data transfer between each module. So here we can see from antenna, the signal is getting received, then it is transmitter part which receives the signal and that goes through the radio front end, and then ADC, that is analog to digital converter, converts the analog received signal into digital, and then it is processed from the host. So this is the high level overview of other components which are there in the RF front end and SDRs. So this is having a central processing unit. This is handling the high level control, signal processing task, and software operation. So next is the FPGA and DSP boards. So FPGA and DSP boards are used for high speed signal processing and hardware acceleration. Then digital to analog and analog to digital converter, that is used for converting digital signal from receiving from the host to transmit that signal. So that is digital to analog converter, and in reverse situation we use ADC, that is analog to digital conversion. And then we have a phase locked loop, which is for frequency synthesis, as it ensuring precise and stable timing for communication. Then we have RF front end. So this RF front end manages up conversion, down conversion, filtering, and amplification of RF signals to and from the antenna. Okay. So these are the application area of SDRs. So basically, it can be used for test and measurement, then radar communication, 5G, 6G communication, advanced wireless system design, spectrum monitoring and recording, medical applications also. They are like SDR can be used in advanced imaging system, wearable devices, and wireless medical telemetry. So then we have satellite communications also. So there are multiple uses of SDR. So in short, we can say SDR are not just radio; they are powerful, reconfigurable platform that accelerates innovation across multiple industries. So this was about the SDR. So USRP is also a kind of SDR. So USRP, that stands for Universal Software Radio Peripheral. It is designed by NI and ITUS Research. ITUS Research is also a part of National Instrument Company, which is completely focused towards providing wireless solution like USRPs, designing USRPs. So USRP software defined SDRs provide software defined RF architecture that allow you to design, prototype, and deploy wireless systems with customer signal processing. These systems are scalable and support multi-channel synchronization, this making them suitable for wide range of research and industrial application. So in terms of capability, USRP supports a frequency range from 1 megahertz to 7.2 gigahertz, and it can be extended up to 8 gigahertz. So that is possible with USRP X410. Okay, we'll go to that also. So for development, USRP devices are compatible of most of the popular software tools like LabVIEW, MATLAB from MathsWork, then open source also like C, C++, and GNU Radio. So this is compatible with all the popular toolboxes for which is used for designing the wireless systems. So one of the standalone feature of standout feature of USRP is the ability to program the FPGA. So USRP comes with FPGA boards also, so that the processing will be faster in case we are using the FPGA programming. So FPGA programming can be done using LabVIEW, can be done using open source and MATLAB also through HDL coder. Hardware options are also diverse, that is ranging from low-cost entry-level radios to high-performance system, and with open FPGA for advanced research. So in short, we can say NIUSRP is a complete family for fully user programmable SDRs that combines general purpose processor, field programmable gate array, that is FPGA, and RF front end. So this combination enables to quickly design, prototype, and deploy next generation wireless systems. So, so here is the brief about USRPs. It starts from low cost or entry level USRP, that is portable also. So the series is starts from USRP B200, B200 Mini, B205 Mini, and B210. So these are USRP having 1 and 2 channels, like 1 transmitter, 1 receiver for B200, and B210 2 transmitter and 2 receivers. So it covers the frequency range from 70 megahertz to 6 gigahertz. So almost you see every USRP is covering the similar range up to 6 gigahertz. Okay, so the lower so then we have after B series, that is basic series USRP. So then we have E series USRP, that is embedded series USRP. So these all USRP E series and B series having a bandwidth, maximum bandwidth 56 megahertz instantaneous bandwidth. Next we have USRP X310 or USRP 2955 is the similar model with twin RX and GPSDO. So twin RX and UBX, these are the daughter boards. So this USRP X310 that comes without daughter boards. Okay, so it comes with the FPGA board and the motherboard. So on top of that, you can put your own router boards like UBX or twin RX. So that depends on how you want to configure. If you want 4 RX channel, then you can use twin RX. And if you want two transmitter and 2 receiver, then you can use UBX. So in UBX router board, you are getting 160 megahertz instantaneous bandwidth, and in case of twin RX, you are getting 80 megahertz of bandwidth. It covers the range from 10 megahertz to 6 gigahertz, and UBX is covering the range from 30 megahertz to 6 gigahertz, and it is supported on multiple platforms like LabVIEW and open source and MATLAB also. So this is USRP X3, that is for X series, X310. So next, there is N series, that is network series USRP, that is for making the system like these are having LO setup also. So you can use these N series USRPs for phase synchronization also. So that devices are N320 and N321. It is having 2x2, and USRP N310 that is having 4x4. That means 4 transmitter and 4 receiver channel. So it can go from 10 megahertz to 6 gigahertz, and USRP N320 or 321 that goes from 3 megahertz to 6 gigahertz. So there we can see the difference in the bandwidth only. So the bandwidth for N310, that is 100 megahertz, and N320 that is 200 megahertz. So next we have the high-end USRP series, that is X4, 4th generation USRP, that is X410. So it covers from 1 megahertz to 7.2 gigahertz and having bandwidth 400 megahertz. So for deploying 5G, 6G test beds, so this USRP fits the best. Okay, then we have X440, which covers the range from 30 megahertz to 4 gigahertz. So it is having 8x8, means 8 transmitter and 8 receiver channel, and it is having a bandwidth 1.6 gigahertz. So it's best suitable for satellite communication, and also for ISEC kind of application where you need more receiver antenna to gather the signal and compare them for ISEC applications. So these are the USRPs available from NI. National, and then one more USRP, that is USRP N2974. So this USRP is having 160 megahertz bandwidth that covers from 10 megahertz to 6 gigahertz. So this USRP 2974 and X410 that can be used standalone also. Standalone means you can program the FPGA, and it is having a real-time Linux-based OS installed inside the USRP. So you can use it as a standalone USRP also. So next, we have the toolbox, like how it works with tools like MATLAB, LabVIEW, and open source. So in case of open source, you can use C++ or Python programming with GNU Radio for general purpose design. And if you want to design FPGA, then you need Xilinx Vivado, that is software, and RFNOC via GRC. Then we have maths work. So MATLAB, wireless test bench communication system support package is there for USRP. That is wireless test bench and communication support package for USRPs. For general purpose design, that is required. And in case we are going to do the FPGA programming, so in that case we need wireless test bench and HDL coder and Xilinx Vivado. Xilinx Vivado is the third-party software, so it makes a loop between Xilinx Vivado and MathsWork. So then it provides the complete FPGA solutions for using USRP. Then we have LabVIEW. So using this is also a popular toolbox. This is from National Instrument itself. So LabVIEW, which is providing the general purpose designs like modulation techniques on software that you can do using LabVIEW. Then we have LabVIEW FPGA for programming the FPGA boards of the USRP. So this is next. Till now we have solution up to 7.2 gigahertz. So, but this is the high, and for this is used only for research purposes. That is PXI based vector signal transmitter, VST. So VST is the next generation, and for basically for the research purposes. So it can go up to 54 gigahertz of frequency range, and it can have the instantaneous bandwidth of 4 gigahertz. Okay, so this is the comparison table of first generation, second, and the third generation. So recently, PXI 5842, this is the third generation USRP, third generation VST system. So there you will get 30 megahertz to 26.5 gigahertz frequency range. So you can upconvert that frequency up to 54 gigahertz. And it is having 4 to 6 slots, and it can have the instantaneous bandwidth up to 4 gigahertz. That depends on your usage and other accessories. So this was the specification of BST. Okay. So thank you so much for your attention. That concludes my part of the session. So now I would like to hand it over to Mr. Praful, who will walk you through the MATLAB and USRP workflow in details.
Sure. Yeah, thanks, Anu. So for covering some of the introduction and giving an overview of NI, USRPs, and VST. So this is for the rest of the talk, I'll very quickly go over wireless system design in MATLAB, software-defined radio support. We'll look at some examples, how you can interface USRPs, how you can look at signal detection, targeting the USRP and generating HDL code, as well as AI for wireless. Some of this, since we are short on time, so I think I'll go over some of these examples and share those with you. The presentation we can share with you following the talk as well, so you have access to all of the links, all of this. We'll talk about some of the courseware and learning resources as well. So in terms of wireless system design in MATLAB, so this is a general block diagram of a wireless system. I'll not go over it, but it requires multiple skills, including architecture design, design of algorithms, to software, to digital hardware, to mixed signal hardware, and RF design as well. So MATLAB and Simulink are a unified platform. We have tools for modeling and simulation across different parts of the wireless system, whether it is for designing scenarios, algorithms, or waveforms. So there are some standard-based tools, 5G, LTE, satellite communication, radar toolbox, signal processing toolbox, which you can use. There are newer tools like the 6G exploration library and the wireless network simulation library as well. There are tools for RF design, for RF PCB, RF toolbox, RF block set, mixed signal block set, tools for antenna and antenna array design, for tools for modeling the channel. This is essentially the standards specific channel models, which are there for 5G, LTE, wireless LAN, or satellite communications. Tools for interfacing with hardware like SDRs or other instruments, RF instruments, or looking at tools for deployment on generating HDL code, such as the wireless HDL toolbox, HDL coder, verifier, SoC block set. And in addition to this, tools for optimization, parallel computing, and machine learning. So all of these make MATLAB and Simulink like a unified platform for the design of your wireless systems as well as applications. Today, we'll primarily be focusing on this aspect, which is the hardware interfacing with wireless tests. I'll not go over this, but depending upon, as I showed you, you could model and simulate communication systems for various levels of connectivity, whether it's Bluetooth, local area networks, cellular networks, or satellite or global networks. You could also look at modeling different parts of the system itself, whether it's the baseband components to your infrastructure, to your UEs or mobile devices, to your applications, which are enabled in 5G or 6G. So let's get to SDRs with MATLAB. So Anup already gave you a definition of what an SDR is. So this is how the IEEE defines it. A radio in which all the physical layer functions are software defined. And when using it with MATLAB, this is how a general block diagram view would look. So the SDR has your RF front end, the antennas, and the onboard processor, an FPGA, which does the DSP. And it's typically connected to the host PC, which runs MATLAB via Ethernet, USB, or other protocols. So we've supported SDRs for quite some time. So we introduced USRP support in 2010. So it's quite mature, and that has continued over the years. So this is almost a decade and a half of supporting SDR. So this is quite mature in MATLAB, and you could work with it. So there are multiple ways in which SDRs are supported. So there is the communications toolbox, which supports SDRs, some of the lower end SDRs and the ones used for teaching, like from analog devices or the NI, some of the USRPs, the 200 series. Wireless test bench, which supports some of the higher series, the N320 and the X series, which were there. And as well as instrument control toolbox, which supports the VST and other instruments from test and measurement instruments from Keysight. And if you want to design your own radios using FPGAs and your own custom RF front ends, there are tools like the SoC blocks. Again, depending upon what your application is, you might want to pick one. I've put in links to each of these at the bottom of the page, and this format is there on each of the slides. We'll primarily focus on USRPs and the communications toolbox hardware support package, as well as the wireless test bench. To install these packages, you might have to, so in addition to MATLAB, you might have to look at the drop-down in the add-on section and click on Get Hardware Support Packages. So this should give you separate support package installation options for USRP, from the communications toolbox and the wireless test bench. So depending upon what USRP you have, you can install these. So let's come to the examples of USRP itself. So there are multiple workflows which are supported. We'll talk about three major workflows. First is just interfacing with the USRP and either transmitting information from MATLAB or taking information and bringing it into MATLAB for processing. The second workflow where you're looking to intelligently capture signals based on some met criteria. So here we'll see how we can capture IQ data, do some very quick processing on it, and then based on, say, detecting the preamble or or the energy of the signal exceeding a threshold, how we can trigger capture. Or the third workflow that we'll be talking about is if you're developing your own signal processing algorithms, your own communication algorithms, you would go ahead, how can you go ahead and prototype those on the FPGA of the USRP? Right. So let's jump in. For the first one, the radio I/O, I'll open up MATLAB and show you quickly some of these examples, but you can transmit and capture data at full device rates, which are enabled by the USRP, which is up to, say, 500 MSPS. You can stream IQ samples to and from MATLAB, and you can also sort of look at streaming in data to the onboard memory of the USRP and then transmit it or receive it. So if you're looking at what are some rates or what are some capacity that we can capture data over, so you can capture, say, up to 17 seconds of 5G data at 30 MSPS, 6.5 seconds of WLAN data at 80 MSPS, and nearly 2 seconds of full N321 device rate, which is 250 MSPS. I saw some raised hands, so if you could put in any questions on the chat or the Q&A section, that would be great. we'll address them towards the end. Right? So let us jump into MATLAB and go over some of this. Here we'll look at transmitting some waveforms which are generated in MATLAB, and then we'll also look at a very quick model of how you could use Simulink to work with USRPs. Yeah. So let me just go ahead and use that. So in the MATLAB window, so you have, so if you want to generate any standard, specific, or custom waveforms, you could look at using a very quick app known as the wireless waveform generator. So it's in the app section of MATLAB. And if you look at the wireless waveform generator, it's in the signal processing section. So there's the wireless waveform generator. I already have it open. So there are various options available for generating waveforms, whether it's 5G, LTE, WLAN, or satellite, and so on. You can also generate custom QAM, PSK, or just sine waveforms as well. So I've selected the 5G uplink fixed reference channel waveform, and then we'll look at how we could go ahead and work with it. So some of the default parameters are mentioned here. You have your the physical uplink control channels and the shared channel, which are indicated here, depending upon what options you select. So you can go ahead and change some of these configurations. Like, so if you want to say change where the PUSCH is located, say it's on the lower bandwidth edge, so it will go ahead and change it to the lower bandwidth edge as well. So you could see how the resource blocks are, as well as and how the slots appear. So you can generate some of these waveforms. And in addition to this, you can go to the transmitter section and directly select the USRP for which you want to transmit it, whether it's the N300 to N320 and so on and so forth, or the other USRPs, the B series, E series, or N series. I'll not go ahead and use this and do the rest of it, but feel free to just open the wireless waveform generator and play around with it. In addition to that, if you're working with Simulink, you can go ahead and design the same thing in Simulink with either a transmitter or a receiver using Simulink using drag and drop blocks. So in this case, I'm generating a bunch of bits, modulating it as per QPSK, and giving it a RCT filter, and then transmitting it to the USRP. So the USRP location is specified from this block, which I can set which sort of USRP it needs to be, its IP address, and so on and so forth. I can add other visualizations such as the constellation diagram and so on and so forth as well. So these were some of the examples which were linked. Otherwise, the radio setup you could also do with code, which is very simple to do. I'll not go into that at the moment, but we'll go ahead and look at some of this later. There are multiple examples for you to get started with. If you are working with multiple USRPs and want to synchronize those, there are examples for that as well. And then how do you capture like an entire 1.6 gigahertz bandwidth using multiple antennas and so on. I hope that covers some of it. We'll look at an intelligent capture in play. So in this case, say you are, so there are radio signals all around, but we need to capture when the signal of interest, right? So a common method is just looking at detecting the preamble of the signal. And so in this case, there are pre-built images for pre-built FPGA images which enable preamble detection. You can modulate some of this preamble detection settings as well. So you can do this for WLAN, LTE, or 5G. Right? I'll go very quickly over some of these and some of the details of how it is implemented, and then you can and share with you the examples. Right. So what we are essentially doing is for the preamble detection, either we are giving the raw IQ data which is captured to an FIR filter. So the FIR filter length is dependent on your sampling rate or what you decide to do, set out. And we are also looking at integrating the signal to look at uh, creating a threshold. So we are looking at maybe signal energy in some sense. So we use the integrator to either and provide it with either a fixed threshold or an adaptive threshold. So now that threshold is compared to the output of the FIR filter. And if the output goes above the set threshold, signal acquisition is triggered. Okay. So essentially what we are doing is we are correlating the preamble, correlating a known preamble to the raw IQ data and then sort of acquiring the data. You can also put in a trigger offset. So if you want to capture not just the preamble as well as the signal of interest, you could have a negative trigger offset so that you acquire the entire thing. So this is what it looks like. So this might be the out for a fixed threshold. So the blue signal is the output of the programmable the FIR filter, the output power, and you can see you put in a threshold depending upon your you can depend upon your radio gain and so on and so forth. Yeah, and you can get the peaks are indicated by where you are able to detect the preamble and trigger acquisition. The same thing for an adaptive threshold. You have your adaptive threshold offset to remove any under like low level signals or correlations, and then you trigger acquisition only when the adaptive threshold is met. And the adaptive threshold moves. So this is the peak. This smaller peak is for the adaptive threshold moving up. But so yeah. So then this peak also is sort of removed. So instead of 2 detections, it just gives you 1 detection. Right. Yeah. So there are examples covering both of this, and these are there in the documentation. I'll not go over this again in the interest of time. I had these open, but we'll just move ahead and look at the examples themselves. So some of these are available here. So you can use these for spectrum monitoring applications where you are where you're waiting for signal capture and responding to when a particular signal transmission is detected. You could create, say, things like the WLAN activity scanner or detect empty channels for transmission. So for cognitive radio applications where you want to sort of look at identifying areas where there is space for transmission, you could go ahead and look at some of those. Right. Finally, for USRP targeting, so here what you would end up doing is you would whatever your algorithm, so you would go from MATLAB to Simulink. You would then go ahead and create a design under test. So for those under from the VLSI background, so I think so you'll create a design under test, which is essentially the logic of what you want to implement, and interface it with the IOs, which is how you would want to transmit data in, as well as transmit the output of your algorithm out. And just the design under test, you will generate HDL code from it, and create an IP core, which you then dump onto the FPGA and have it run on the full device rate, which is there. Again, it's quite an involved workflow. So there are multiple steps here. But I think for high-speed applications, this is worthwhile. This is something that you would need to do. So how does that work? So for example, so in this case, the FPGA has your RF front end as well as your programmable part. So suppose I'm doing some sort of spectrum calculation or spectrum computation. So then what I would do is I'll design the logic for spectrum computation, because that's just doing an FFT and then computing the spectrogram. And then that logic, I'll create an IP core out of it, and that will go on to the FPGA. If you wanted to uh, then transmit things back to the host, which is the host PC, you could again go ahead and package that as well. So I'll go ahead and very quickly open up an example, a couple of examples to do this, because this is something that is relatively new and something that you might not have seen. So yeah, so this is an example of, so we'll go over two examples. One is just a simple multiplier. So in this case, yeah, so in this case, this is just a simple multiplier. What we have is a Simulink model where you go ahead and get data in. We simply add some gain, essentially multiply, and then package it up, and then sort of get back to what the output was. So if you look at what the gain is, it's essentially taking in data. It is converting it. It is uh, converting data types and simply multiplying it with the input gain which is there. So whatever gain input which you received, you're simply multiplying it, concatenating some of this output, and then just giving it out. Okay, that's simply the logic, right? Simple gain, simple multiplier. So you can sort of control what the gain is like, and you can go ahead and use this. So if you hopefully this runs the visualization, and you will see how things work on this. So you could go ahead and um, look at some of the outputs. Yeah. So this is what the outputs look like. So this is the input real and imaginary data. You can see the scale is 0.4 to 0.5. And this is the output data, which is from -2 to +2. So, so the multiplying factor was 4. It went from -0.5 to +0.5 to +2 to -2. So we haven't generated the IP core, yet. But what we will need to do is, if we have, we will simply need to go look at the apps and look at the HDL coder app in Simulink. And all of these instructions are available in the example. So we'll go ahead and look at that as well. So in the HDL coder app, you can go ahead and look at selecting that particular model. So I'll demonstrate that very quickly. Yeah. So this is what it looks like for maybe a spectrogram computation. So you have the input data coming in, the design under test, which is your spectrogram computation, and then your external MATLAB interface. So here in the design under test, you can go ahead and look at, so you have multiple aspects here. So you're just computing FFTs through FFT blocks, and you are just computing the spectrogram from that. So in this case, we'll go ahead and you just have to, once you select HDL coder, you can select the block for which you need to generate code and just generate IP code. So a window will pop up and guide you through the rest of the steps. So again, I've linked these examples here. There are additional examples as well in terms of how you could do custom OFDM on the USRP, how you could do radar target emulation for integrated sensing and communications, or JSAC applications, as well as how do you do FIG NR detection. So finally, we'll talk about AI for wireless. We'll look, so you could do multiple things here in terms of generating signals or capturing over the air signals and bringing it in, pre-processing some of these signals like the spectrogram computation or the, like we just saw, developing some of these models and then deploying them onto hardware. Again, there are multiple examples on this front which we could go over, but there are a lot of capabilities in terms of that we offer in terms of both designing AI models, interfacing with Python, and interoperating with them, as well as fine-tuning AI models and deploying them onto hardware. So this is one application that where we are looking at AI for wireless using USRPs. This is again as part of the wireless test bench, where we are doing some rough sensing of presence detection in a room, depending upon the CSI information which is there in the wireless segments. So CSI or channel state information is something that we obtain, and we just convert it to a spectrogram and generate some training data and use that to identify whether there is someone in the room or not. Okay. So uh, so this is using wireless waveforms. So you can see these are some spectrograms of no presence data, where there is no one present in the room. So your WLAN waveforms are just coming from your router to your USRP, and you can see what the spectrogram looks very clean. But as soon as there is someone in the room and there is movement in the room, movement of people in the room, the spectrogram sort of changes up, because there is because the channel is different, right? And that changes the CSI information. And you could simply give these to a deep neural network and use it to detect whether there is someone present or whether there is not. This is a very simple example, but there are a lot more examples on spectrum sensing and so on and so forth as well. There is a full 6G research and development 6G exploration library, which enables you to look at a whole broad range of capabilities around millimeter wave and sub-terahertz communication, new waveforms, non-terrestrial networks, and all of the RIS and all of these other capabilities which are there. In terms of courseware, there are some teaching resources on digital communications, on advanced communications, as well as multi-carrier modulations. Some of these are from very well-known names, Sandeep Rangan at NYU Wireless, or Ana Garcia Armada at University of Carlos III in Madrid. There are a bunch of self-paced courses as well as instructor-led paid training courses which are available. If you're new to MATLAB or Simulink, so if you're new to Simulink, there are courses available which you can use or your students can use, and how you can work with streaming signals. And there are also courses on wireless communications. There's a full paid training course, a 2-day paid training course for USRPs with MATLAB using. So this is delivered virtually. So you could go ahead and take that as well. That's about it. That brings us to the end. Hopefully we are on time. So thanks for your attention, and yeah, let us take any questions that you might have. So anyone who has any questions or any clarifications that they would want, please feel free to. So yeah, so I can see a couple of questions there. Okay, let me take them one by one. If we are not able to handle anyone, we can come back to this and reach out later. So so USRP supports only communications toolbox or 5G toolbox as well. So again, USRP support is there. So USRP support is there for all of the so USRP support is there in general for 5G toolbox as well. So any of the waveforms that you generate, you can go ahead and transmit using MATLAB. So there is satellite communications toolbox. So if you generate satellite waveforms like your NAVIC or GNSS waveforms, you could go ahead and generate, you also interface that with USRPs, or Bluetooth waveforms, you could do that as well. So calibration accuracy. Okay. So Manish asks, since the SDR hardware is not factory calibrated, how should we handle calibration when using it with MATLAB and Simulink for RF development and testing? And what is the best accuracy that we can expect compared to calibrated RF instruments? Okay. So I'm not sure how exactly to handle that. So one thing you would do is, yeah, I think I might have to get back to you on that. One thing you would do is like, so when you're looking at USRPs, so essentially you are measuring with the, so for USRPs and SDRs, you are essentially looking at measuring in the full scale dB, which is there. If you need dBm measurements, it would be good to move to typical RF test and measurement instruments, right? So yeah, so that's maybe the short answer. I can sort of investigate this a bit more and then sort of get back. So if you see, like, if you're looking at validation or testing, so maybe something where power is of concern, then I think test and measurement hardware is your go-to rather than SDRs. So DAB support. Okay. Can you maybe clarify what DAB is? So sure. So while okay, so we are using SDR-based QPSK examples from the help document. One SDR with a is desktop and MATLAB 25A is going, and there might be I am not sure. So Vardhana Reddy, so if MATLAB is crashing, yeah, please write to us. So my email is ppi@mathworks.com. If you are facing any issues, please feel free to write back. Or one thing you can do is if you are crashing, so on the home side, go ahead and request support. Yeah. Okay. Yeah, Manish. So he says digital audio broadcasting. Okay. Yeah, sir. So I'm not sure. So on the interfacing with some of the other open source tools, I am not sure how to kind of answer that. Again, so this is something that I'll maybe need to get back to you on, whether there is something there on the audio broadcasting. I'll capture this question and then definitely get back to you. If you could maybe put your email into the Q&A, and then I think, or we, then that would be great. How can we optimize USRP parameters for reliable AI-based wireless experiments? Again, like I think so some of the parameters like radio gain and so on, so these are accessible to you. So for example, if I show you one example in MATLAB, so this is the wireless sensing example what I was telling you about. So some of the USRP gains, USRP parameters are available to you, like gain, offset, the radio gain, some channel numbers, and the frequency bands, and so on and so forth. How many captures you need to make, and so on. So there is no good way to optimize. I would say there's so because every time you change some of these parameters, you might have to reset your acquisition. So what you might need to do is you have to find the best parameters initially for your environment, for the current testing environment you are in, and then once you find that through some initial captures, then you go ahead and use this, right? And the thing is, since you are trying to design algorithms for different environments, so first you test it with one controlled environment, then you test it with another controlled environment, then you test it with a third controlled environment, and all the three environments are different from each other. And yeah. Yeah, so there are some questions on system requirements in terms of RAM to run our 16 GB machines hang when we run Simulink files. So yeah, I would say that's something that we are completely we are working on over and over to improve in terms of system requirements and so on. One thing I would recommend is like so I think my laptop has maybe 32 gigabits of RAM, and I think that's MLA. One of the few options that you can play around with is maybe go to the settings and go to the amount of memory that you can manage here. So there are options to sort of manage the memory here, and you could provide it with more memory instead of the default. So that's one way. Unfortunately, there's no better one. I would again also, yeah, maybe this is again something while not related to USRP. Maybe this is again something that there are other ways to maybe look at accelerating some of the Simulink models, but yeah, beyond a particular sized model, your memory requirements will go large. So maybe clearing out some of the existing variables and working with those. I think that those are your best options. But I'll maybe reach out to you, Professor, and then we can discuss more on that. Yeah. Yeah. Any additional questions? I know we are slightly over time. Thanks for sticking around. So
Praful, I think we have some more questions in the question and answer section.
sure, let me just.
I think Sat took care of some of them.
Sure. Yeah, I think whether you can use an external camera with USRP and whether any other intermediate instruments are needed to connect. So yeah, so I think in terms of external camera with USRP, like so essentially you might want to do image. Let me just go ahead and I'm sorry. Sure. Yeah, sorry about that. Yeah, so I don't know what happened, but if you want to transmit images, I think what might be a good example is, so there is an example for transmitting transmitting like information, like so transmitting an image, so which you can maybe use. Yeah, so I think it is this particular example. Yeah, so there is maybe, I think it's this particular example on LTE transmitters. So which transmits an image, and then you can sort of go ahead and work with that. Yeah, so so there is an example on image transmission which you can use. I think that's maybe the short answer for it. Any tool for verifying handover scenarios? I think so. If you're verifying handover scenarios, I think that's more on the network simulation side. You can use USRPs there, but again, I think so the network simulation library might be a better option there. So there are examples around that. So if you just search for wireless network simulation library and 5G or 5G system level simulation, uh, uh, then that would be good. Since it's not the topic, let's not look at that. Yeah.
Right, that was very insightful. Thank you, Praful. I think we also breached the time limit that we had set for ourselves. So it's time to call it wraps. I'd like to thank both of you, that is Ayush and Praful, for your insightful presentation. And all participants, thank you for your active participation. And we truly appreciate your time and engagement. And we hope this session has been informative and inspiring for your research and projects. Now, of course, if you have any pending questions, you can always reach out to us at contact@digitotech.com or sales@digitotech.com. We'd also be sending you a link to collect your feedback. So you can also share your queries. And if you'd like us to contact you, you can share your phone numbers on that form with us. Thank you all once again. And I hope you have a nice day.
Thanks, everyone.
Yeah, thank you.
Thank you, Anu. And thank you, everybody, for joining.